Welcome to today's webinar. Our webinar today is how final element design and selection relates to overall SIF performance and cost. I'm Chris O'Brien. I'm a partner with exida. I've been working in functional safety and automation for over 30 years. I help our customers, both OEMs and end users, with the design and implementation of systems, and I'm happy to be the webinar leader today. So today we're going to look at the significant impact that final elements have on overall performance of a SIF. And it's the performance from a safety reliability and a process availability perspective, but also in the overall lifecycle cost. We'll cover what the drivers are when selecting a final element, how that selection can affect maintenance costs, and learn about new solutions and ways to address that, such as exida's new eRAVA certification program. exida is a customer-focused company. We really focus on three main areas: enterprise tools, certification and assessment, and lifecycle services. All of those are tightly related and reinforce each other, and we really try to bring a pragmatic approach to helping you solve your problems. For many years, we've been playing defense when it comes to final elements and functional safety. A lot of our efforts, exida's efforts, and the industry efforts have been on trying to avoid errors and mistakes being made that result in really unsafe systems being installed. And that's still very important, and there's still quite a bit of work to do in that area. But we are making progress. The word's getting out. People are becoming more knowledgeable, and lots of companies, both equipment suppliers and plant owners, have made tremendous strides in that area. And this is just a slide I like to use to show that, not all final elements are created the same, not all are maintained the same, and it's not to say that the solution on the left can't give a good result. But a lot of that work then is going to go on the integrator and user of that to make sure that happens. The concept we'd like to introduce is integrated process risk maturity model. So it's a classic maturity model based in 5 stages, going from really not a great deal of expertise over in the ostrich phase, moving all the way to a proactive or pretty sophisticated advanced solution. And as you move from left to right, you're kind of moving from growing to the point where you're doing the right things, because all the way to the left, if you're not aware of the standards or kind of just viewing them as attacks, you might not even be doing activities you do need to do. And as you move towards the center where you're kind of becoming competent, maybe phase or milestone 2 or milestone 3, where you're becoming capable and being able to do it in a repeatable manner, all the way to the right side where you're in kind of a advanced state and being proactive. You're collecting data, you're making evidence-based decisions. You've kind of moved from doing things right to doing the right things. So that's just a general classic maturity model, and we've taken it and we've applied it to functional safety, alarm management, and cybersecurity. So if we really look at all 3 of those things, we can say, how do all those things work together to increase plant safety? I started with that photo. So a lot of work, as I said, has been done in that defensive stage, or helping customers who weren't aware that there were problems or drivers, or have a problem and they need somebody to help them triage it. So a lot of work's been done there. We've done a lot of webinars on those types of subjects, and we want to start helping people move to becoming, best practice and proactive in their approaches. So we want safety to go up and the cost of achieving it to go down. So that's what we're going to focus a lot on today, are what are key levers that you can take advantage of to begin and continue your journey towards the right. I've grouped it into 3 things. So we can talk about fault avoidance, failure avoidance, failure reduction, and failure detection. So failure avoidance is really, we could think of it as classically what might be called systematic failures, things that can only be corrected by process or procedure. But some of those fall into design-related failures, and some fall into application-related failures. So design-related failures could be improper specification, either of the system or of the device being designed. Application failures could be a failure that results from applying the wrong device or in the wrong application. So we're going to talk about methods to avoid and minimize those. Failure reduction, there are ways to get better failure metrics from existing devices. So those things are often the random failures or randomly occurring failures, and there's a few techniques that we've developed that we're going to discuss about how can you get lower failure rates for devices in a justifiable and maintainable way. And then finally, failure detections. We know we're not going to get rid of all failures, so how are we going to detect them and correct them before they defeat the system? If we look at currently what I would call a properly designed automation solution, I'd say that's right in the middle of the maturity model. We give credit in the assessments and in our failure rates for well-designed, engineered industrial products that are properly applied. So that is, if you're using, say, the standard failure rates that come with the device, you're using Excellentia, you're doing the normal stuff, you're getting results. Those results are indicative of what you would expect in your plant. We've calibrated that with over 350 billion field hours worth of failure data. So we're really comfortable that that's kind of honed in and a good result. We are not in the left-hand side. We're not over here on the left where we've got that really unpredictable or unrepeatable thing, but we really haven't gotten as far to the right as maybe we could. So today we want to talk about moving to the right. Some key drivers that relate to maturity level or how maturity level relates to them. If we're thinking about avoidance, it's going to be the failure rates of the product and the reliability of the product, but that really is going to relate to the selection of product. And over at maturity level 0 or ostrich, we might just be using generic failure rates. If we move to the right, we're going to talk about new solutions that are in the eRAVA or exida remote actuated valve assessment category. So we're going to move through a continuum where we're using generic to using certified components to getting an integrated solution to maybe getting a certified solution. Our next point of focus is going to be here in this column or this row that we talk about reduction. And if we're looking at reducing the failure rates, so you've picked the right equipment, but can you justify a reduction? And this concept of site safety index has a big impact on the failure rates you should select. And also there's an advanced analysis, a safety reliability analysis that can be done on products that may justify a further reduction. And then finally in the diagnostic and test realm, the testing that's being done really frankly could be none. There are still people who have safety systems and don't have them on a periodic testing regime. And again, as we move from the left to the right, we could go from no testing to typical testing to following what's in the safety manual, and all the way to the right, we're going to be then looking at optimized testing results. So if we look at this maturity level 2, or right in the middle for final elements, what does that look like? What should you be doing if you're taking failure rates out of an FMEDA report or out of Excellentia and using them? You should be using well-integrated and designed assemblies that have probably at this point a semi-formal verification and validation technique. You should have typical plant capabilities when it comes to testing and maintenance, and you should be make sure that your devices are implemented and tested per the requirements of their safety manuals. So to move past what would be considered maturity level 2, what should you consider? You should consider using certified assemblies that have a formal verification and validation techniques. look at process improvement in your plant that would move you from maybe a site safety index of 2 to maybe a site safety index of 3. And then make sure that the assembly you have has a safety manual for the assembly that's providing you kind of optimized testing information for that. Proof testing information, that is. So first thing I want to talk about is eRAVA. So that stands for exida Remote Actuated Valve Assembly. That is a new program we've introduced in the last year, and it goes through a final assembly assessment, so the assessment of a complete final assembly. I'll talk a little bit about what we cover in that. What that does is it basically reduces the variability and the risk associated with the assembly, and that provides you a more reliable solution. What's included in that is a comprehensive review and assessment of all the things in that. So eRAVA has multiple things that we look at, and we look at multiple things in detail so we can provide a good assessment. So at the top level, we look at a deep dive of functional requirements of the assembly, application requirements of the assembly, detailed design specification. Again, all of these are at the assembly level. Design verification, a fit for use evaluation, manufacturing capability, integration of the assembly, integration verification, then installation and operation and maintenance instructions. If we expand that a little bit and just take a deep dive, so let's just take a deeper dive into design verification. So on the left-hand side, we've got our normal flow chart for an assessment project. And then with the eRAVA, we're going to go into that assembly. And let's say we'll take, as I mentioned, design verification. Under design verification, we're going to have multiple more detailed requirements we're going to look at, such as, is there a verification plan? Is the fail direction defined? Is it going to be a long standstill or only cycling once a year or so? What are the fluid characteristics? What are the operating temperatures? And then we could take torque, and this is just an example. All of these have greater detail, but for example, under design verification, we would have torque, and we would be looking at things like break to open torque. What's the break to open breakaway angle? What's the run to open torque? Run end to open torque? Break to close torque? Run to close torque? And further. So for each of these subcategories, we're going to have a requirement that we're going to review and make sure is met, and that the OEM has standards and practices to cover them, and then also publishes that information in a way such that the user can ensure that it's going to meet their requirements. In addition to the eRAVA, we also have a safety reliability analysis, and that's one where a detailed analysis of components can be done, which may justify lower failure rates as well if a specific component within a device is designed to withstand the stresses or the application better, then it's going to have a lower failure rate. If we look at safety culture or SSI, that's another big driver. We can realize that human factors play a big impact of safety performance. You have things such as imperfect repair, improper calibration, faulty installations. These and other factors are going to decrease the overall safety performance, and Site Safety Index is a way to measure that. So Site Safety Index is something that exida has come up with, and we use it to adjust metrics. So we could think of a typical plan as being Site Safety Index 2. If you improve, you might be Site Safety Index 3, and a perfect plan would be Site Safety Index 4. But you could also be less than typical, and then you might be down at a Site Safety Index of 1 or 0. So it's a way to adjust typical failure metrics to which assume typical performance to either give credit for or to provide some safety margin for less than ideal conditions. This allows sites with a strong process to take credit for that, and also allows sites that need to do some growth having accurate data map their site. This is just a little bit of a summary of the difference between the different ones. You can find this on our website, but Site Safety Index 2 is good. Repairs are usually correctly performed. There's procedures in place. If we move up to 3, it's almost perfect. They're correctly performed. They're done on time and on schedule. And 4 might be an ideal, but it's unlikely that any plant really, or it's a challenge for a plant maybe to be perfect. So theoretically it's possible, but it might be a pretty hard lift. Another thing that really can impact the safety and cost is improving diagnostics and testing. So when we think about testing, especially for final elements, so a lot of our equipment, safety equipment, comes now with a lot of built-in diagnostics. So if you're buying a safety transmitter or you're buying a safety PLC, there's going to be a lot of things that have been done on that system, but they're embedded in it and you kind of get it with the system. For final elements, there is a lot that can be done, but a lot of times that's going to be more on the end user to ensure it's done correctly. So the first thing you need to know is, well, what are you looking for? If you don't know what you're looking for, how to find it, it's really kind of going on a scavenger hunt. You're not really sure which failures or failure modes contribute the most or what effective testing is. So you need a strategy. This ties in very closely with the eRAVA approach and the FMEDA approach, because an FMEDA is going to go from component by component in the device, and it's going to build up those failure modes, those faults, all the way up to functional failure modes for this component, for the device. And by knowing that and having that analysis, it's possible to map out the failures within the device to specific tests that could detect them. Now that test could be done automatically, like an automatic partial valve stroke test. They could be done manually, like a partial valve stroke test, or by like a leak test. Either way, the more important thing, it's important that they're done, but it's also important to map out those failures and be able to properly allocate the failure modes, the failures to the failure mode. So here's kind of an example summary where those different functional failures, excessive force, loss of drive, leakage past the seat, spurious or safe failures, detectable failures and no effect, have been mapped out. And for final elements, we've got 5 proof tests proposed, starting from the simplest, which is a partial valve stroke test. Number 2 is a full valve stroke test. Number 3 is a full valve stroke test in operating conditions. 4 is a full valve stroke test and a leak test offline, and 5 is a full valve stroke test and a leak test at operating conditions. And you can see that for a valve body, your overall diagnostic coverage can change pretty dramatically, or dangerous detected coverage can change pretty dramatically. So having this information and designing your proof tests accordingly can really give you much better reliability, but also help you optimize and run those proof tests when they're needed to be done. So if we start implementing these things, what kind of results can we expect? Well, one, if we eliminate those systematic failures or we increase failure avoidance, we can significantly reduce design issues. And I would categorize design issues as a misapplied product or an issue with a product, and an application issue resulting in putting a product in a situation or a process that it's not going to be capable of doing. Second is we can reasonably anticipate a reduction in failure rates. We've done several eRAVA assessments as well as safety reliability analysis, and getting a reduction of the failure rate from 20 in the range of 20 to 30% is reasonable. And with designing the failure, the proof testing and the diagnostics, we'll get a good alignment of the effort used in the testing regimes to the results. So how do we get started, or how can someone get started? So you can begin, if you're an end user, you can begin looking for OEMs that are supplying certified integrated assemblies. If you're an OEM, you can investigate getting your entire assembly assessed. If you're an integrator, you could look at the same thing. You could ask the supplier. Either way, this works for supplier or plant owner. Share more application information between both parties. You can evaluate your site safety index. We've got a survey you can take online. If you go to our website, we'll give you an idea of where you probably fall. You can begin performing functional safety assessments 4s. Document how are your systems performing over time, collect the data in the plant and evaluate it by application, review proof test results and strategies, as well as all the other steps that are very important in an FSA 4. With that data, you can begin to optimize a proof test design, and exida is always available to help with functional safety assessments, as well as doing benchmark studies where you are now and give some recommendations for how to improve it. But you can see that if we can begin to pick the right gear, start getting lower failure rates because we're picking well-engineered gears for our application, optimize our test investments, we really can begin to increase our safety and reduce our cost. So I'd like to thank everybody for attending and pause now for people to ask questions. Be happy to answer them. Thank you.